math humans. We're going to do 1.3a today. We're going to be talking about limits analytically. So our objectives are that we're going to evaluate limits graphically and analytically. So from yesterday, remember that the limit of a function as x approaches a constant is equal to some value L if and only if the limit of the function as x approaches c from the left is equal to the limit of the function as x approaches c from the right. And then remember that yesterday we talked about a couple of cases where limits did not exist. So as we do our first example, it says evaluate the limits. Okay, and in this one, I'm going to give you a couple of different graphs. So for the first one, we're going to have this graph, and this is going to be a horizontal line, and it's going to be, I'll put it like that. There's a 3, okay, and then this is x is equal to 2. So I want the limit of the function as x approaches 2, and because this value is defined, it's going to be 3. And so that means that regardless of what x value you picked, the limit would always be 3. So that's kind of cool to think about. So then the next graph is going to be a cute little line, and this is going to be y is equal to x. And I want to know what happens as the limit approaches a negative 4. Well, I can do f of a negative 4, and I get a negative 4. Right? So that would be the y value right there. So then the limit of the function as x approaches a negative 4, and I'll continue the line a little bit, from the left and the right is going to be a negative 4. So that would be technically considered graphically, but we're also being able to substitute a value in, so it can also be considered direct substitution. All right, the next thing that we're going to do is a little bit of just defining things. We're going to talk about the properties of limits. And the first one is that the limit as x approaches c of b times f of x. So if I have a constant on the inside, that's the same thing. I can pull that constant out front as x approaches c of f of x. And remember that we talked about the limit, oh, you can't see it, the limit of a function is L, so that's going to be our standard. So then this is going to be b times L. The second property would be if I have the limit as x approaches c of f of x times g of x, then that's just going to be the limit as x approaches c of f of x times the limit as x approaches c of g of x, okay? And then that would be, remember the limit of this one is L, and we're going to define the limit of that guy is k. So I would just multiply the limits of those two things together. Number 3, the limit as x approaches c of a function divided by another function would just be L divided by k, okay? Number 4, the limit as x approaches c of f of x plus or minus g of x, and you're going to guess it, is just going to be, we can split this up, the limit as x approaches c of f of x, and then plus or minus the limit as x approaches c of g of x, which is going to be L plus or minus k. Alrighty? And then the last one that I have, number 5, is the limit as x approaches c of a function raised to a power is just going to be the limit raised to a power. And we don't need to memorize these, but occasionally we will use the properties to help us find a limit. For example number 2, I want to find the limit as x approaches 2 of 4x squared plus 3. Now, before we start, we could break this up. And we could break this up to be the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. And we could do direct substitution. So 2 squared is 4 times 4, so this would be 16 plus 3, which is 19. Or you could just do direct substitution. And here would be that case. This is just a cute little parabola that looks like that. So basically, there's nothing that's undefined. So I would just do what I would consider to be direct substitution. And from the very beginning, I would say the limit as x approaches 2 of 4x squared plus 3 is going to equal 4 times 4 plus 3, which is 19. And then I would report, remember we have to make a conclusion statement always, is going to be of f of x is 19. So if you can do direct substitution, hallelujah, that means your math is really easy. If, on the other hand, you can't do substitution, that's when we have to bring in other methods. Example number 3, I want to find the limit as x approaches 1 of x squared plus x plus 2 over x plus 1. Now, if you'll remember on this one, if we think about the graph, I'm going to have a slant asymptote because the degree in the numerator is higher than the degree in the denominator, and it's going to be about y is equal to x because x goes into x squared x times, okay? I'm going to have a vertical asymptote at x is equal to a -1, and so I could do this graphically. But because this is a positive one, when I substitute it in the bottom, the world doesn't explode, so I'm just going to do direct substitution. So this is 1 squared plus 1 plus 2 over 1 plus 1, 2, 3, 4 over 2 is 2. And so that's actually really simple. So if you can do direct substitution and the world doesn't explode, just do direct substitution because it makes our life so much simpler. You could put this in your grapher and look at the situation. It would look something like, and remember we have to be very careful with parentheses, I would have a vertical asymptote at a -1. I have a slant asymptote here, and then at the value 1, this curve's going to go this way, this curve's going to go this way, and that value would be 2. Okay, so that's what it would look like if you did it graphically. Most of the time, we're going to do these either analytically or through direct substitution, okay? All right, so let's go back and review a little bit of trig before we do our next problem. So this is just a little bit of a reminder. The sine of an angle is y over r. The cosine of an angle is x over r. The tangent of theta is y over x, okay? The cosecant of theta, which is the reciprocal of sine, is r over y, and I remember it by the letters don't match. The secant of theta is r over x, and the cotangent of theta is x over y. Okay, and just since we're here, I'm going to also remind you that if I have a 30, 60, 90, opposite to 30 is 1, opposite to 60 is radical 3, and then the radius is 2. And then if I have a 45, 45, 90, this is 1, 1, radical 2. So the expectation is that you will be able to find coordinates, and we did a lot of that last year. If you are struggling with this and having a hard time remembering, you can go back and watch my pre-calc, and it would be like 4.1 to 4.3, I think, in the videos if you need to go back and review this material. All right, our next example is going to be example 4. And I want to find the limit as x approaches 0 of the tangent of x. So I'm going to actually do this a couple of different ways. So remember that tangent has asymptotes, and tangent's period is pi, and it has asymptotes at half of that, right? And so this would be 3 pi over 2. So my graph is going to look something like this. There's my other little guy, okay? But I'm also going to consider it from here because this is the unit circle and this makes my life easier. So tangent of 0, this is 0 degrees. Tangent is y divided by x. If I do direct substitution, I get that the tangent is 0. Party over. So remember that tangent of x is y over x, sine over cosine, which is 0 over 1, which is 0. So therefore, the limit of the function as x approaches 0 is 0. Yay, that was easy. We like trig. Next example, example 5. I want to find the limit of x cosine of x as x approaches pi. So since I'm going to be needing to do the cosine of pi, I'm just going to sketch pi. Remember, pi is here. His coordinates are -1, 0. Cosine's not undefined anywhere, so I think I can just do straight direct substitution. The limit of x when x approaches pi is pi. The cosine of pi is a -1. Therefore, the limit is a negative pi. Woo, that's easy. So the limit of the function as x approaches pi is a negative pi. Well, that was pretty easy. All right, we have one more example, and then we're done for today. Example number 6. We're going to do a problem that we did yesterday or the day before, and we're going to talk about it from a different perspective. So x cubed minus 1 over x minus 1. You do need to be able to factor cubic binomials, and the way that you do that, it's always going to be the cube root and the cube root, and then it's going to be the first term is squared. The second term is not doubled, as it is if it's a binomial, and then there's my last one. These are easy to figure out. If you need to redistribute to figure out your signs, then you can do that. Okay. Here was the x minus 1. The x minus 1's cancel, so remember that means I have a whole at x is equal to 1. And then I would just do my direct substitution, okay? So at this point, and here's where I made a mistake, so let me kind of draw a line right here. I needed to have the limit as x approaches 1 in here, because this was my whole point about this. You have to carry, when you're doing a problem analytically, the notation all the way through the problem until you do the direct substitution. So what I should have done is written this as the limit as x approaches 1, shown that I had rewritten the problem. You have to show all steps. It's almost like doing a proof. You can't skip steps. And now I could do my direct substitution. 1, 1, and 1 is 3. And then I can write my conclusion statement. The limit of the function as x approaches 1 is 3. So our analytic work is going to become a little bit more entertaining. But if you choose to factor something, you have to show, and then you have to carry this notation until you are completely done and do the direct substitution. And then you need to write your conclusion statement. All right, that's it for today. I will see you soon.